Okay, this is Unit 12, Lesson 5. We're going to work on something called the law of sines. And then there's something I need to mention at the beginning of these notes that is very important. And this carries on for the next 3 or 4 lessons. The triangles that we're working with are not right triangles, meaning they still have 3 angles. Those angles still add up to 180 degrees. However, we are not assuming that we have a right triangle. So if we don't have a right triangle, we don't have a hypotenuse. We just have 3 different legs. And if we don't have a right triangle, we cannot use the Pythagorean theorem. So very, very important things just to keep in mind as we start in on these next 3 or 4 lessons. So law of sines works like this. Given a triangle ABC, the following ratio is true. Sine A over A is equal to sine B over B is equal to sine C over C. So just a notational thing that is really, really important to note. Angle A and side A are always across from each other, like this. The same way that the hypotenuse is across from the right triangle or the right angle. We just don't have a right angle. So angle A is across from side A, angle B is across from side B, angle C is across from side C. So when you're setting up the law of sines, what we are saying is the sine of an angle over its opposite side is the same ratio throughout the entire triangle. Okay, so we can use this anytime that we have an angle side pair. Okay, so this idea, all of this, we can use side and angle measures if you have 2 angles and any side. So if you have like A and B and then any of the 3 sides, or if you have 2 side lengths and an angle outside of them, meaning like C and A and not this one, but like either of the other angles. So what it comes down to is that you need an angle side pair. Okay, very, very important. You need an angle side pair, meaning you need both angle A and side A, or both B's or both C's. Okay, so let's start off with an example. Number 1, if you look here, we have an angle side pair. We have this 34-degree angle, which is across from this 10. So we set up the ratio. So we set up sine of the 34-degree angle divided by its opposite side, which is 10, is the same as this next ratio, the sine of the 52-degree angle divided by its opposite side, which is x. And the x is what we're trying to solve for, so we're going to do a little bit of algebra here to get that x by itself. So what we are going to do is cross multiply. We will multiply this numerator by this denominator. So it ends up being x times the sine of 34 degrees equals, and then multiply these two. So 10 times the sine of 52 degrees. We get x by itself by dividing both sides by the sine of 34 degrees. Remember, sine of 34 degrees is just a number. Like it's a complicated decimal value somewhere between -1 and +1, but it is just a number. So people make mistakes in reducing. They think that they can like cancel out the word sine, which you can't. They think that they can reduce down the 10 and 50, or the 10 and 34, the 52 and 34. You can't do any of that. You just want to plug this in exactly the way it's written. Otherwise, we could make a mistake. So we are plugging in 10 times. Now, anytime you do trig, check your mode. Even when you close out of the app and then reopen it, it tends to reset to radians. So double check every time you use Desmos that you are in degrees. I sometimes make that mistake myself and then I get a wrong answer. So sine of 52, close the parentheses, divided by the sine of 34. Now this, if the constant kind of ends up over to the side, format-wise, that's okay. Just make sure that these are divided by each other, and then we get this value. Directions say round to the nearest tenth, so it would be 14.1. Okay, so that's what it looks like to find a side. So either the angle side or the angle side angle case. This was the kind of angle, not really angle side angle. This is more of the angle side case. Okay, so that was one example. Let's look down at question number 5. We have a little bit of a story problem here. You see this setup. It's 3 guys passing a hockey puck around. So they are standing in 3 different locations. We measure the angles between them. We also measure the distance between these 2 guys. Question 5 asks, how far is Kevin from Adam? So here's Kevin, here's Adam. Let's label this distance with an X. That's what we're trying to find. So when we set this up, we need a pair. So we do have a pair right here. The 86-degree angle is across from the 25-foot side length. So we can set up that first ratio just like we did with number 1. equals, and then if we're looking for this, we need this. So we don't have that, but it's okay because we have the other two angles and we know that all triangles add up to 180 degrees. So it's a very easy fix to find the piece that we're missing. So if they all add up to 180, that means we can subtract these two from 180 and we'll get our leftover piece. So this must be a 23-degree angle. So as soon as you add that in, then we automatically have that piece and we can go from there. All right, so this, we now have the sine of 23 degrees. So this is technically the angle side angle case, even though it works just as easily as this one. So over x, we're now looking at the exact same setup. So this was just a touch more advanced than number one because you had to find one of the missing angles, but then the setup is identical. So we're going to solve it just like we did number one. We cross multiply here. We have x times the sine of 86 degrees is equal to 25 times the sine of 23 degrees. And then just like number one, we divide both sides by this value of sine, which just gets plugged into a calculator. It's just going to be a long irrational number if you were to plug just that piece in. So this cancels. I get the x by itself on the left, and I'm going to plug this right-hand side in just the way it's written. So 25 times the sine of 23 divided by the sine of 86. Okay, so round that to the nearest tenth, I get 9.8. And this is a story problem, so they mentioned those distances were given in feet. So if there are units, make sure you include them in your answer. All right, next topic, starting on the next page, we're going to be finding angles. So this would be the side-side angle case. We're going to talk about a couple of very, very important things here, and we're going to reference back to our unit circle when we do that from the previous lesson. So finding angles, we have this little watch out warning here. It's going to remind us of some things we discovered in our last couple of lessons with the unit circle. When you are finding angles using the law of sines, it's possible to have either one, two, or no solutions. We refer to this as the ambiguous case. So some facts that we're going to use as we work through a couple of problems here. The sine function always has a range between -1 and +1. That's really important. If you take the sine of an angle, it's never going to be any smaller than -1. It's never going to be any bigger than +1. It's always somewhere in between. So look at the unit circle for that. This is the largest y value, which is 1. This is the smallest y value, which is -1. We never go outside of that range. Next, if the sine function is positive, the angle can lie either in the first or the second quadrants. To find the other possible angle, subtract from 180 degrees. So I'll reference something that we talked about in our last video. So if we look at 30 degrees, for instance, the sine of 30 degrees is 1/2, but we also mentioned that 150 degrees has the same exact value, but your calculator is automatically going to give you the easier one, the lower one, that's in quadrant 1. So if you find 30 as one possible angle, do 180 minus 30, and you get the other possible one. Or say you did 60. 180 minus 60 would give you 120. So if you subtract from 180, it gives you the other possibility. One other thing we talked about on the previous page, the sum of all three angles is always 180 degrees. And finally, no triangle, because of that, can have two obtuse angles. Remember, obtuse angles are bigger than 90, so you can't have two obtuse angles within the same triangle because they always add up to 180 degrees. So you might not have any obtuse angles, but at a maximum, you can only have one. All right, so we're going to do a few examples right here. We are going to work with example 8 first. Okay, so they give us some dimensions here. We're going to just do a little sketch. I am terrible at sketching these to scale, so just work with me here. So angle B is 37 degrees. Side AB, let's call this A right here. So AB would be 47. AC would be this one right here, which is 29. And then we want to find angle C, which would be this angle right here. Okay, so we write down all of those pieces, and then we are going to set up our law of sines. Okay, so we have a pair right here. So we set up the sine of 37 degrees divided by the side length of 29 equals, and we're looking for C. We do have its opposite side, so we can do the sine of C divided by 47. All right, so we don't quite cross multiply here because we just need to get the C by itself. We just take the 47 and multiply it over to the other side. So we do that. multiply the 47 over to the left, and that leaves sine C by itself. So this is kind of what we're solving for right now. We're going to plug this left-hand side into the calculator. So we want to write it down exactly as it's written. Quickly double check. You might as well do that each time, especially if the app closes out. Sine of 37 degrees divided by 29. So this is a value of sine, somewhere between -1 and +1. You want a bunch of decimals on there. I usually like to get in the habit of doing 5 or 6. So 0.97535 is the value that we get for sine of C. And now remember, when we have the value of sine and we're solving for the angle, we do inverse sine. Okay, so do that inverse sine key, and that will find us the actual value. So inverse sine of 0.975355. So this, let me see, is not the value we should be getting. Oh, sorry, I did sine, not inverse sine. Let's try that again. Inverse sine of 0.975355. There we go. So rounds the nearest tenth, we have 77.3 degrees. So C is equal to 77.3 degrees. So that is the value that's in the first quadrant. To find the angle that's in the second quadrant, we subtract from 180 degrees. So, or we do 180 minus 77.3. And we get 102.7. So this is a possibility as well, because watch what happens. If I take the sine of 102.7, I get that same exact value that I had right here. Just remember, your calculator is automatically only going to give you the one in the first quadrant, so we have to check to see. Now, the last thing is that we need to use this piece of information, that no triangle can have two obtuse angles, so we need to see if these two could even fit within the same triangle. If we add these together and we go over 180, they can't possibly fit together. But these two fit together and don't go over 180, and these two fit together and they don't go over 180. So it actually is possible here that we could have two different measurements for angle C. All right, so we always need to check that. Let's look next at number 9, see what happens there. So set up our little triangle here, sketching all the pieces. So angle C, see, I'm terrible with scaling. They always look like equilateral triangles. So angle C is 75. AB would be on the other. So like this would be A and this would be B. So this is 28. AC is this side, which is 19. And then find angle B, which would be this dimension right here. Okay, so opposites. Set up the sine of 75 degrees over 28. And then the other pair, we have the sine of B over 19. So this part gets solved the exact same way we did with number 8. Take the 19 and multiply it over to the left. And that gets sine of B all by itself on the right-hand side. And then we want everything we have on the left to just be plugged into the calculator. So 19 times the sine of 75, divide that by 28. We want a bunch of digits here. All right, so I'm going to write down 0.65544, actually that would be 450, would round up. So that's the value that we have for sine. And remember, we do inverse sine to figure out what our value of the angle actually is. So next I'm actually going to press the inverse this time, 0.655450. So that would be 40, and then 0.95 would just round up to 41. Okay, so 41 degrees, or, so that's the first quadrant. We can find the corresponding angle in the second quadrant by subtracting from 180. We get 139. So, or 139 degrees. So again, let me prove this to you. Sine of 139, oh my goodness, there we go, gets the exact same value of sine. Your calculator just kind of predetermined will only give you the first quadrant value. So these, there's room for both of those because those don't go over 180. But if I try to add these two together, I go over 200. So there is not room for both of these within the same triangle. So even though it would technically work, it won't fit in the same triangle. All right, one last problem here, number 10. So this is 114, so that I could sketch. 114, we've got this obtuse angle here. AB is 34, BC is 12, then it says find angle C. So that's this one right here. So we have our opposites. So we set up sine of 114 degrees over 12. equals, and then the sine of c over 34. So just like the previous two, start by multiplying that 34 over to the left, equals sine of c, and we plug that left-hand side into the calculator. Okay, so we get 2.588378 is equal to the sine of c. Now we come across the problem that we had up here. Sine is only between -1 and +1. If I get something that's bigger than 1, it ends up being no solution. Like, watch what happens if I try to do inverse sine. 2.588378. It says that it's undefined, which means there is no such angle. This is the case where you have no solution. If you look at these, like look at this dimension, it should hopefully make no sense to you that this side would be much smaller than this side when it's across from a gigantic angle. So these dimensions couldn't possibly work in a triangle. So because of this right here, we say there is no solution. So we saw one example of each, 0, 1, and 2 possible solutions.